So, hello class. We are going to continue our lecture on learning graphical models from data. Until now, we have covered 8 classes of learning algorithms. And all these classes of algorithms were for Bayesian networks, which are directed graphical models. Okay. So if you remember, there were 3 dimensions that we looked at. The first dimension was what type of learning we are doing, whether it's MLE or maximum likelihood estimation or Bayesian learning. If you remember, in the Bayesian learning, we have a prior, while in the maximum likelihood estimation, we don't use a prior distribution over the parameters. Then we saw another dimension, which was whether we were learning the parameters of the Bayesian network given data, or we were also learning the structure of the Bayesian network in addition to the parameters. So in this case, only data is given, but the structure of the Bayesian network is not given. And we are trying to estimate both the structure as well as the parameters. And the third dimension that we looked at was what type of data set we have, whether it's a fully observed data or FOD or partially observed data or POD. Okay. Today we are going to switch gears and look at undirected graphical models or Markov networks. And look at both parameter as well as structure learning algorithms for Markov network under various assumptions, such as whether we have partially observed data or fully observed data, or whether we are doing maximum likelihood estimation, right, or doing Bayesian learning. Okay, so let's begin. So here is what we will cover. We will first cover the basic case, which is learning the parameters of a Markov network given structure associated with the Markov network. So whenever I say that the structure of the Markov network is given, I am talking not only about the graph structure, but the precise description of the potentials or the precise scopes of the potentials. Okay, so when we looked at the representation for Markov networks, we saw that the primal graph associated with the Markov network is not unique in the sense that it does not describe the scopes of the potentials. Okay, so in this case, whenever I'm talking about parameter learning, I'm assuming that the precise scopes of the potentials as well as the graph structure is available to us. Okay, so we will look at the most basic case first, which is fully observable data, and we are doing either maximum likelihood estimation or Bayesian learning. We are going to look at 2 types of algorithms, one which are generative, which learn generative models from data. Essentially, if you think about it, let's say that the variables in the graphical model or the data or the variables that you're interested in are divided into 2 categories, where let's say X are the so-called observed variables and Y are the so-called unobserved variables, or the variables that you want to predict. Okay, what the generative model does, it learns a joint distribution over both X and Y. What the discriminative model does is that since you're only interested in predicting the values of Y given X, so X is always assumed to be known, and therefore it learns this so-called conditional distribution for all values of X from data. Then we will slightly complicate the problem and look at learning the parameters of a Markov network from incomplete data or partially observed data using both the MLE as well as the Bayesian approach. And finally, we will cover approaches that learn the structure of the Markov network from data. So as you'll see that in the Bayesian network case, structural learning was very complicated. And the reason structural learning was complicated was that Bayesian networks are directional. So we always have to be very careful about the ordering used. Because as we saw, different orderings can give us different IMAPs. In Markov networks, since they are undirected models, we don't have this ordering constraint. Okay, so structural learning algorithms are simpler. But as we'll see, unlike Bayesian networks, the parameter learning algorithms are extremely complicated. Okay, so the good news, there's good news and bad news, right? The good news is that structural learning is slightly easier. Okay, but the bad news is that the parameter learning is way harder. Okay, so that's the preview, and now let's dive into the details. So what we're going to do is we are going to look at an alternative parameterization of Markov networks, and this is done for convenience in the sense that the gradients that we'll compute will have a nice convenient uh, or I should say like their expression look quite nicer as compared to the potential form. Okay, so this is the parameterization we are going to use. The parameterization is nothing but we are going to express the Markov network as a log linear model. If you remember, we studied log linear models when we studied representations. Log linear models are defined as a set of weighted features, where let's say fi is the feature and theta I is the parameter associated with the feature. Okay, and the distribution associated with the log linear model is given by the expression that is given on the slide. So given an assignment x to all variables, the log linear model, the probability of that assignment is nothing but the normalized exponentiated sum. Okay, and the sum is over the product of the parameter and the feature. Okay, so one way of interpreting this is that if the assignment x evaluates the feature to true, then its weight is counted. Otherwise, its weight is not counted. Okay, so this representation we saw when we looked at uh, various representations of probabilistic models, and this is what we are going to use. Okay, so I'm not going to go into the details of what this representation is because we have already covered it in the class. Okay, but the point being that we are going to use the log linear representation and talk about features and weights associated with the features, right? And that's why sometimes parameter learning is also known as weight learning in Markov networks, right? Because you're learning the weights associated with the features. Okay, so now let's look at the first and the easy case, which is doing generative weight or parameter learning under the assumption that the data is fully observed. Okay, so if you remember, the task here is to learn a distribution p of x, where x is a set of variables, and this is a fully observed data case, right? So every variable in x is observed in your data set. The task here is to learn p of x by maximizing either the likelihood, if you're interested in the maximum likelihood estimation approach, or maximize the posterior probability if you are interested in the so-called map approach. Okay, so let me preview what this case looks like. The preview is that unlike Bayesian networks, and this is an unfortunate thing, we don't have a closed form solution for the parameters, even for the FOD case. Okay, And as a result, what we have to do is we have to use iterative optimization algorithms, such as gradient ascent, I should say, right? Because we are maximizing here to solve the problem. There is some good news, and the good news is that similar to the Bayesian network case, right? We will have the likelihood function is such that the likelihood function will only have one global maxima. Okay. Another way of saying this is that the likelihood function is concave, right? And therefore, the objective function for in our learning as optimization is a concave function, and therefore we are guaranteed to reach global maxima if we use an algorithm such as gradient ascent with appropriate etas, right, or appropriate so-called step sizes. Again, the bad news, okay, the bad news is that you will see that when we derive the gradients, that we are going to require inference at each step of gradient ascent, and therefore our algorithms will be very, very slow, and so we'll need some methods to speed them up. Okay, so to summarize, unlike Bayesian network case, FOD or unlike Bayesian networks, right, parameter learning in the FOD case, parameter learning here is extremely complicated. Okay, so let us derive it. So what we're going to do is we are going to derive the derivative of log likelihood under the assumption that we have fully observed data and we are maximizing the likelihood. So let us set up the problem. We are given a log linear model, which is defined as that, right? So log linear model is nothing but a set of weighted features, fi and theta I, okay? And we are given, let's say, a data set which has m examples in it, right? So this one denotes the first example, then there is a second example, and so on, and now that one is nothing but the mth example. So let us write down the expression for log likelihood given the data and the model. So the model is described by theta. So think about theta as nothing but this set, right? So this is capital theta, which is the set theta 1 to some, let's say, theta p, right? Where p is the number of parameters. So if we have p features, then there will be p parameters, right? Each feature is associated with a parameter. Okay, so log likelihood is nothing but the log of the product of the probability of generating the point. Okay, so likelihood of one point is the probability of generating that point, and likelihood of the full data set is nothing but the product of the probabilities. Why? Because we are assuming again that data is IID, or independent and identically generated. Okay, so since they're independent, the probability of the data set is nothing but the product of the individual probabilities. So taking the log inside, right? So substituting, let me erase some drawings here. So what we can do is if we substitute p theta, right, which is that expression in here, right, and then we know that log of products is nothing but the sum over logs. Okay, so if we do that and move the log inside, okay, there is another, then we get, sorry, there is a double sum here for some reason. Then we get that we are going over the data set, right? So this is nothing but the sum over the data set, log of the probability. Okay. So we know that log of x times y is equal to log of x plus log of y. Okay. So what I can do is I can expand this expression. So that becomes log of 1 divided by z theta, which is nothing but minus log of z theta. Okay, so that will give us that term. So then the first term is The other term in the product is nothing but log of exponent of this sum. Okay, and log of exponent is nothing but that particular quantity, right? So what you're going to get is that sum over there. So that's how I got the sum here. Okay, so now what we have is there is one quantity which does not depend on the data at all, right? Because z theta is nothing but the partition function, because theta is already given to you. So what I can do is if I move the sum inside, then that just becomes m times log of theta. Okay? The first term here becomes a double sum, and since sum is commutative, what I can do is I can put the I outside, right, instead of inside. Okay, so now this log likelihood expression becomes sum over I theta I. Okay, so this sum over I is nothing but sum over all the features, the weight associated with that feature, which is nothing but theta I, multiplied by sum over the data, whether the feature is true or not. Okay, so one way of looking at this is that fi of x, if you're given an assignment, will be equal to 1 if the feature is satisfied in the data point, and fi of x will be equal to 0 if the feature is not satisfied in the data point, right? Or another way of saying this is that if the data point x evaluates the feature fi to true, right, then the output is 1, otherwise the output is 0. Okay, so in a way the expression inside is just counting, right, how many times the feature is true in the data. Okay, so another way of saying this is that the expression inside, right, so I should just focus on that expression over there, is nothing but the expected value of the feature according to the data. Okay, what I'm also going to do is express the log likelihood in a more convenient form by dividing both sides by m. Remember, this is an objective function, so if we scale the objective function if we scale the objective function by any value, right, the solution, the optimal solution will not change. Okay, so I can actually divide both sides by a constant, right, and I will have no effect on my gradient ascent algorithm, right, or the optimal solution that is being reached by my gradient ascent algorithm. Okay, so the bottom line is that I can express the log likelihood as this particular sum, right? And the sum has this nice intuitive form. The intuitive form is that the objective function is nothing but the sum over the features, right? Sum over each feature weight times the expected value of the feature according to the data, okay? Minus log of the partition function, which is log of z theta. So if you remember the gradient ascent algorithm that we are going to use for solving this problem, since there is no closed form solution, the main step in the gradient ascent algorithm is nothing but computing the derivatives. Okay, so computing the gradients, right? So let us try to take the compute the gradient or the partial derivative of the log likelihood with respect to theta I, which is one of the parameters. Okay, so remember the big set theta is a large set of all the parameters, and what I'm doing is I'm taking the partial derivative with respect to one of the parameters. Then let's call that parameter as theta I. Okay, so based on the previous expression that we had, right, let's take the derivative of the quantity here with respect to theta I, and the derivative of the quantity here with respect to theta I. What is the derivative of the quantity here with respect to theta I? Easy, right? So this is a sum over thetas, right? So one way of writing this is like you have theta 1 times expected value of the feature f1, right, plus theta 2 times the expected value of the feature f2 according to the data, and so on and on and on, right? So this is a sum. All of the terms, right, except theta I expected value of fi, right, are constant, right, because we are taking the partial derivative with respect to theta I, right? So all of these terms will disappear when we are taking the derivative, and the only term that will remain is this one. So this is nothing but derivative of x times some constant. So what is that? That is nothing but c. Okay, so the output of the first term will be equal to the expected value of fi from the data. Okay, so this is nice and easy to compute, because this is nothing but the number of times a feature is true in the data. Okay, the second expression is slightly complicated, because we are taking the derivative of the log partition function, right, or the log of the partition function with respect to the parameter theta I. So let's do that. So recall that z theta is given by is nothing but the normalization constant, right? So you're going to sum over all assignments x, exponential of, so this is nothing but the weight of the assignment, or the value of the assignment. The weight of the assignment is nothing but exponentiated sum of theta I times fi of xi. Okay, so this is nothing but the sum over all feature weights that are evaluated to true by the assignment. Okay, so now what we're going to do is we are going to take the partial derivative of z theta with respect to theta I. Okay, so let's do that. Right, so partial derivative of or I should say log of z theta, right, not just z theta, but log of z theta with respect to theta I. So partial derivative of log of z theta is nothing but 1 by z theta times the derivative of z theta. So this is same as saying that derivative of log of f of x, right, is equal to 1 divided by f of x times derivative of f of x. Okay, so f of x is nothing but z theta here, right? So that's why we have this expression. Okay, so let's now substitute z theta here. So what we have is sum over all the assignments x, right, times the weight, sum over all the assignment x, right, the weight of the assignment. So I can move the derivative inside, right? So for each assignment x, I'm taking the derivative of the weight of the assignment with respect to theta I. Okay, so that is nothing but we have to take derivative of exponential of f of x, which is equal to exponential of f of x times the derivative of f of x. Okay, so what we have here is the original quantity times the derivative of the quantity inside. So that's what we are going to take, right? So derivative of this quantity we already know is nothing but fi of xi. Okay, and what I'm going to do is I'm going to do a simple manipulation where I move the z theta inside. Okay, so if I move that z theta inside, then this is nothing but the expression for p theta of x. Agree? This is nothing but the probability distribution that is represented by the log linear model. So this is equal to sum over x, p theta of x, fi of xi. Another way of looking at this is the definition of expectation. So if I take the expectation of the feature according to my log linear model, right, I'll get this expression. So derivative of log of z theta with respect to theta I is equal to the expected value of fi of xi according to the current model. Okay. So now putting these two terms together, if you remember, we had two terms, right? The derivative of the first term turned out to be the expected value of fi of xi according to the data, and the derivative of the second term turned out to be the expected value of fi of xi according to my model. Okay. Another way of saying this is that the first expression is nothing but the number of times the feature fi is true in the data. So you can make one pass over the data and calculate this and store this somewhere. The second expression is the expected number of times the feature fi is true given the current set of parameters theta. Okay. So now the question is, how do I compute this guy? This guy is easy to compute, right? There's nothing but like just make one pass over the data and compute the counts. Okay. What about this one? This one is hard to compute. Why? Because I have to run an inference algorithm. Okay. So if I want to compute the expected value of fi of xi, what I have to do is I have to compute, let's say the feature is nothing but x and y. I have to compute the probability of x and y according to my model. How do I compute this? I can compute this by setting x and y as evidences and running the variable elimination algorithm to compute the probability of x and y. Okay? This is hard to do because this requires us to solve sum product inference problems. And in the worst case, these might be exponential. Why? Because unless p is equal to np, right, and we can solve sharp p hard problems easily, or someone proves how to, or tells me how to solve these sharp p hard problems easily, in the worst case scenario, right, we'll have to spend exponential time complexity to solve the problem. Okay, and that's why I said that gradient descent algorithms are going to be very slow, or gradient ascent actually in this case, because since we are maximizing, are going to be very slow. Okay. Anyways, let's look at a simple gradient ascent procedure, since we already have a way of computing the gradients, right? The way the gradient ascent procedure will work is we start with the random parameters, and at each iteration t, we update each parameter theta I t by using theta I of t plus 1 is nothing but theta I of t plus eta, which is the learning rate, right, or the step size, times the gradient. And the gradient is nothing but the expected value of the feature according to the data. This can be pre-computed. And the expected value of the feature according to the current set of parameters theta t. Okay, and this, right, this expectation requires us to run inference over the model. Okay, so what I just described to you, right, is a way of estimating the parameters of a Markov network given its structure, right, using the gradient ascent algorithm. Why did we need to use a gradient ascent algorithm? The reason was quite simple, because we did not have a closed form solution. Okay, and to summarize, right, the log likelihood function is still unimodal. Okay, so if the gradient ascent procedure converges, assuming that the learning rate is small enough, then what we are going to do is we are going to actually reach the global maxima. Okay, okay, but in the worst case, the algorithm that I just described to you, the gradient ascent procedure, is exponential, and the reason it's exponential is because for computing the gradient, I need to run. Sorry, I think I went to the end. For computing the gradient, I need to run exact inference algorithms. Okay, so now let's go from maximum likelihood estimation to map estimation. Okay, and if you remember in map estimation, so now we are in so-called Bayesian learning. So if you remember in Bayesian learning, we put a parameters on the, or I should say, we put a prior on the parameters, right? And then we try to maximize the product of the prior with the likelihood. Okay. So in this case, if we use a independent Gaussian prior or a Laplacian prior, okay, we get like nice solutions. Okay, so let's look at what these priors are. So in the independent Gaussian prior, what we assume that each parameter is associated with a Gaussian, okay, with a given sigma. Okay, so each parameter will be the mean of the Gaussian will be nothing but the value of the parameter. Okay, and sigma is assumed to be a constant. Okay, so sometimes we will write this as P2 of theta given sigma. So that's my prior distribution. My prior distribution is a Gaussian over the parameters. Or I can use a so-called Laplacian prior. And the Laplacian prior, it's again an independent prior. What I do is I put a prior which is exponent of the absolute value of theta I, right, the parameter itself, divided by beta, where beta is an input to the Laplacian prior. So another way of writing this is P1 of theta given beta, right? So beta is given to you, and this is the expression for the Gaussian prior, and that is the expression for the Laplacian prior, right? So the Gaussian prior assumes that the variance is given by sigma squared, while it assumes that the mean is constant, right? And it's constant, it's 1. So in log space, if we look at the product of the prior, right, so let me erase these drawings for a second. So in the log space, if we look at the product of the prior and the data, right, that could be expressed as log of the prior plus log of the likelihood. Okay, and the first term for the two priors, which is log of the prior, is nothing but minus lambda 2, where lambda 2 is a constant, times sum over theta I squared. How did I get this? Simple, right? All I'm doing is taking log of this. What will happen is that this is a constant, right? So that will move out. Sigma square is known to you, so that will also move out, right? And then what I'm left with is log of exponent of minus theta I squared, right, times some constant. So this is nothing but minus theta I squared. Okay, so that's why if I take the log of the first expression, or the log of the log prior is nothing but minus lambda 2, where lambda 2 is a constant, times theta I squared. Similarly, if I take the log of the Laplacian prior, what I get from it is minus lambda 1, which is a constant, times sum over I, the absolute value of theta I. Okay? So remember that in map estimation as well, we are going to use the gradient ascent algorithm to solve the problem. And what the gradient ascent algorithm will need is gradients of the new terms that we are going to add. Okay, so let's take the gradient of this term with respect to theta I and the gradient of that term with respect to theta I. So gradient of this term with respect to theta I is nothing but minus 2 times lambda 2 of theta I. Same principle, right? So one way of looking at this is nothing but theta 1 square plus theta 2 square plus theta 3 square and so on, multiplied by lambda 1. Okay, all the other terms are constant when we are taking partial derivative with respect to theta I. The only thing that will remain is a term theta I squared. And the derivative of theta I squared is nothing but 2 times theta I. So that's what we have. Okay. The derivative of the absolute value of theta I with respect to theta I is nothing but the sine of theta I. And this derivative is not defined when theta I is equal to 0 because we have this so-called discontinuity. Okay. So actually, if you look at how this function works, right? It's a linear function of theta I, so what I'm going to get is something like that, and the derivative is not defined there. Okay, so the derivative of the second term is, or I should say, the derivative of the second log of the second prior is that quantity over there. Okay, and unfortunately, it's not defined as theta I equal to 0. And therefore, we have to use some modifications to the gradient ascent algorithm in order to make it converge to the right quantity. Okay, I'm not going to go over those modifications in this lecture, but you can read any book on gradient ascent or advanced methods, right? Or in fact, for that matter, any machine learning book, and you might, at least like some machine learning books will involve algorithms which handle this case. Okay. Okay. So let's not handle the second case, right, which is using the Laplacian prior. So if we use the first case, the only change in our gradient ascent algorithm, again, I should say, I always use the word gradient descent for some reason because I'm used to it, but I should have used the word gradient ascent here. The only small change in the gradient ascent algorithm that I'll make is that the gradient has now changed. If you remember, the original gradient was that guy, right? And all I'm going to do is just add the new gradient to it, and the new gradient is nothing but minus 2 times lambda 2 times theta I. Okay. There is a second interpretation of these priors, and the second interpretation of this priors is that they are nothing but L2 and L1 penalty. Specifically, we think of the Gaussian priors, or independent Gaussian priors, I should say, as nothing but L2 penalty, right? And the Laplacian independent Laplacian prior has nothing but the L1 penalty. Why? Because if you look at the log, like, or if you actually look at the objective function, the objective function is nothing but ln of p theta, right, plus the ln of the likelihood, which is nothing but the log likelihood. Okay, and ln of p theta is equal to, if we use the independent Gaussian prior, minus lambda 2 times sum over theta I squared. So theta I squared, or I should say sum over I theta I squared, is nothing but the L2 norm. Okay, so what I'm doing is I'm taking my original objective and penalizing that objective. Why am I penalizing the objective? Because I'm subtracting lambda 2 times sum of I theta I squared from it. Okay, so one way of understanding this is that I'm imposing a quadratic penalty on my objective function, right? And that quadratic penalty is nothing but a penalty on the magnitude of the weights. The quadratic penalty, in a way, like, does not like large weights. Why? Because if you think about it, let's say the likelihood was 50. Okay, so let's say I have 2 points, so 2 settings for theta. In the first setting for theta, let's call it theta 1, the likelihood was 50, and let's say for the second theta, the likelihood cannot be 50, but the log likelihood, let's say, was something like 50, and theta 2, and again someone or someone spoke in my ear or something like that, right? The log likelihood cannot be even 50, but let's assume that the log likelihood is 50 just for the sake of understanding like what is going on. And let's say for theta 2, the log likelihood was 70. Okay, so what will happen with theta I squares? Theta I squares will impose penalty. So let's just assume that all the parameters in these theta1 were very, very large. Okay, so what happened was that when I took sum of I, theta I squared, for these sets of parameters, I got, let's say, something like a 40. Okay, so now the new objective is 50 minus lambda times 40. Actually, I made a mistake, right? So let's assume that this is 100. Okay, so we are changing our settings now. Theta1 was 100, the log likelihood, and theta2, the log likelihood was 70. Okay, so if you were using the MLE approach, I would have preferred theta1 as compared to theta2. Okay, but now what happened was that the parameters, right, associated with theta1 were very, very large, right? So the penalty was now lambda times 40. In the second case, let's say the penalty was very, very small because all the parameters were very close to 0 in the theta2 case, and the penalty was something like 2. Okay, so assuming that lambda is equal to 1, the objective, right, uh, uh, according to the new criteria, right, which is objective plus the penalty, will be equal to 60. Okay, and the value of the objective according to our new criteria will now be equal to just 68. Okay, so using the penalties, I'm going to prefer the solution that has a value of 68 over the value of 60. Okay, so this is how you can understand what these penalties are. These penalties are nothing but they penalize the magnitude of the weights. They don't like large weights. Okay, the N1 penalty is similar, right, except that it now imposes a linear penalty on the magnitude of the weights rather than imposing a quadratic penalty. And as you can imagine, like, the quadratic penalty grows faster as compared to the linear penalty. One good thing about the L1 penalty as compared to the L2 penalty is that L1 penalty is linear and quite sharp at 0. Therefore, in practice, what will happen is that it will often yield many parameters that have 0 weights. So if a parameter has 0 weight, it means that that parameter does not exist, right? And we can actually throw away that parameter, right? So what this does, it makes the graphical model sparser. Okay, so now you're given a collection of features, and let's say half of those features have 0 weights. You can throw away those features, right? And you can remove the edges corresponding to those features from the graphical model. So in that case, the graphical model will become sparser. Okay, so that's why N1 penalty is sometimes used for achieving sparsity, and it's also used for doing structure learning, as we'll see towards the end of this lecture. Okay, so we saw two methods for estimating the parameters of a Markov network. One used the maximum likelihood estimation criteria, and the second used the MAP criteria, or the Bayesian estimation criteria. Okay, but both these approaches are unfortunately impractical, and the reason they are impractical is that because when we perform gradient ascent, or when we use the gradient ascent procedures for solving these problems, they require exact inference. Okay, and exact inference, as we saw when we studied inference, can be exponential in the tree width associated with the graphical model. So the worst case, unless p equals np, the algorithms that I just described to you are impractical, right? Or you will need a graphical model that has a small tree width. Okay, so if the graphical model is let's say has tree width 2 or tree width 3 or something like that, right? Then the previous procedures that I described to you were practical, right? Otherwise, they're not. So we can use two approaches to address this issue. The first approach is to use an alternative objective function such that exact inference is not required for those objectives, or exact inference is very fast for those objectives. So examples of such alternative objective functions are pseudo-log likelihood and contrastive divergence. Right? So pseudo-log likelihood is, or pseudo-likelihood I should say, is quite old. I believe it was developed in around 1950s. While the contrastive divergence criteria is a little bit recent and was made popular by deep learning methods. The second approach is to use approximate inference algorithms in lieu of exact inference algorithms. And we saw a large number of approximate inference algorithms when we covered inference, such as belief propagation, sampling-based inference, and map inference. Okay? But there is an issue, right? And the issue is that there is no free lunch. If we use alternative objectives or if we use approximate inference algorithms, we might lose convergence guarantees, or we might lose consistency guarantees. Moreover, the solutions that we find, right? So solution is nothing but a setting of the parameters, right? Setting of all the parameters in the set theta. That solution may have very low likelihood, which means that it's far from optimal if we are using the maximum likelihood criteria. Okay. However, in order to make sure that our algorithms are practical, we might have to use these objective functions, alternative objective functions, and approximate inference algorithms. So let's consider the first case of alternative objective functions. And actually, I'm only going to describe like one case of alternative objective function. If you want to read about contrastive divergence, you can read the book. And that first example approach is pseudo-log likelihood. So pseudo-log likelihood is defined as the likelihood of each variable given its neighbors in the data. Okay. So another way of writing this is PL of x, or the pseudo likelihood of x, is the product of the probability of generating that a variable xi given an assignment of values to all other variables in the data. Okay. So we know that in Markov networks, P of x given others is nothing but P of x given the Markov blanket of x, which is nothing but the neighbors of x. So in the context of Markov networks, we can write down the pseudo-log likelihood, or the pseudo-likelihood I should say, as the product of xi given the assignment projected on the neighbors of xi. Okay. The good news is that if we use gradient ascent, and the expression for gradient is given in the book, I've not described it on the slide, but if you compute the expression for the gradient, you'll realize that when we use pseudo-log likelihood as our objective function, we do not require inference at each step. Okay, so gradients can be computed easily. A good property of the pseudo-likelihood estimator is that it's a consistent estimator, which means that if you have infinite amount of data, eventually you are going to reach the correct solution. Okay, but for finite amount of data, all bets are off. Because of its good properties that it does not require inference at each step of gradient ascent, it's widely used in various applications such as computer vision, spatial statistics, and so on. However, a drawback of pseudo-log likelihood is that the parameters will not work well for long inference chains. Okay, so if your inference chains are very, very long, right? So think about this as nothing but a Markov chain, right? And if you want to do inference over a longer chain, then the parameters may not work very well. Okay, so there are various improvements to pseudo likelihood that are proposed in practice, such as block PL, and the idea here is that you divide the variables into multiple subgroups, right? So you partition the variables into multiple subgroups and then compute pseudo-log likelihood as follows, right? So let's say you have three groups, x1, x2, x3, right? Then pseudo-log likelihood over x1, x2, x3 is nothing but P of x1 given x2, x3, P of x2 given x1, x3 times P of x3 given x1, x2, right? So let's say you have n variables, You have just divided them into three partitions or three parts. Okay, then you can write down the likelihood expression as that. Okay, so this is similar to doing blocking in Gibbs sampling that we covered when we covered a Gibbs sampling algorithm. And typically, when we use block PL, often these the parameters are much better as compared to using the regular pseudo likelihood criteria. Next, what we'll do is we'll switch gears and look at discriminative or conditional parameter learning. So until now, we have only looked at generative parameter learning, and we saw that generative parameter learning is hard, even when the structure of the model is given to us, because we have to do exact inference or use alternative objective functions. So in discriminative learning, what we are interested in is predicting the value of variables in the set Y, also known as the query variables, given evidence or given observations on another set of variables called X. Okay, so here the criteria, unlike the generative case, is to maximize the conditional log likelihood of the data rather than maximizing the likelihood of the data, right? So conditional log likelihood is nothing but P of Y given X. Okay, so you're maximizing the log of P of Y given X, and in the regular likelihood you're maximizing, or the generative likelihood, you're maximizing P of X comma Y, right? So this is the generative case and this is the discriminative case. Again, we can use the gradient ascent algorithm for solving this problem, and the most important thing in gradient ascent is the gradient itself, right? So if you have an expression for gradient ascent, then as I said in class multiple times, you can use software, right, that has been coded by mathematical software experts to solve the problem. Okay, so all you need is an expression for the gradient and you're done. So the expression for the gradient in this case is given on the slide. And one intuitive way in which you can understand this expression is that for each example, right, so the gradient is nothing but a sum over all the examples. And the way we can understand it is that for each example, gradient equals the number of times the feature is true in the data minus the number of times the feature is true according to the model. But not only the model conditioned on the evidence, right? Because we always know that X is given to us. Okay, so as you can see that for computing this is easy because these are nothing but counts in the data. Okay, so that is easy. However, computing the expectations is harder. Why is computing the expectations harder? The same problem as before, right? This requires running inference on the model. However, unlike the generative models, right, where we only run inference just once for each iteration of gradient descent, in the discriminative case or the conditional case, we require inference for each example, right? So let's say the algorithm was run for t iterations and you have m examples, right? In the generative case, you have to run your exact inference algorithms O of t times, where t is the number of iterations for gradient ascent. In the discriminative case, you have to run exact inference algorithms t times m times, where m is the number of examples. Okay, but there is a caveat, and the caveat is that the inference complexity for the discriminative case is much smaller. Why is the inference complexity much smaller? The inference complexity is smaller because a large number of variables might be given to you. So think about it this way, that let's say your Markov network is defined over 100 variables, right? And you're going to assume that, let's say, 90 variables among them are always given to you, and only 10 variables are query variables. Okay. Then your new Markov network, after you conditioned on the evidences, will only have 10 variables. So you're running an inference algorithm over 10 variables in the discriminative case, although you're running the inference algorithm multiple times. Okay. So while in the discriminative case, you're always running inference algorithm over 100 variables. That's why even though you're running the inference algorithm multiple times in the discriminative case, the algorithm might still be faster. One way of circumventing this problem of requiring inference at each time point, or each, not time point, I should say, at each data point, is to use an alternative objective function. And one objective function that is widely used in practice is this voted perceptron-based objective function. And the idea is fairly simple. What you do is you approximate the expected counts in the, so if I erase this drawing, so if you remember that we need this expected counts, so you approximate these expected counts by computing the counts just in the MP state for y. Okay, so instead of solving the so-called summation problem, what you're trying to do is you're trying to solve the maximization problem or the MPE problem. Okay. This voted perceptron approach was first proposed for training hidden Markov models discriminatively in Collins, I believe in 2002. I might have the year wrong. And the form for the gradient is fairly simple. The form for the gradient is that gradient is the difference between the count in the data for each example minus the count in the MPE tuple. Okay, so if you remember, this expression was expected count of Fi given xj. Now what we are doing is we are running an MP algorithm, let's say a local search algorithm, to compute the MP value for y given xj. So once we have the MP value for y, we have a complete example, right? And once we have a complete example, all we are doing is we are figuring out whether the feature evaluates to true according to that complete example. Okay, so that's the expression for the gradient. The gradient is nothing but the difference between these counts from the data minus the counts at the MPE value. This algorithm is often very biased, and therefore in practice what we do is, rather than returning the final answer, right, which is nothing but theta I of t, if we are running the algorithm for t iterations, we typically return the average over all the iterations. Okay, and the average is given by theta I is equal to 1 divided by t sum over t equals 1 to t, where t is the number of iterations, theta I t. Next, what we'll do is we will look at learning the parameters of Markov network under the assumption that the data is partially observable. Recall that here what we do is we are still maximizing the log likelihood of the data, but the likelihood function is no longer unimodal, it's multimodal. Why is it multimodal? It's because we are summing out all the variables that are not observed, right? And we saw this in the Bayesian networks case. Without loss of generality, let us assume that the set of variables is divided into two sets, y, which are the missing variables or the hidden variables, and x, which are the observed variables in the data, right? So what I'm assuming that in each data point, right, y is always missing and x is always given. So in this case, we can again use the gradient ascent algorithm as before, and the gradient is given by 1 divided by n. You go over all the examples, the expected value of the feature given the data point according to my model theta minus the expected value of the feature without the data. Okay, so this gradient is a difference between two expectations, right? The feature expectation over the data and the hidden variables, which is that one, right? Minus the feature expectation over all the variables. And as you can see, this is problematic because this requires inference per data point. Okay, and this requires inference. I should say this requires inference per data point and per iteration of gradient descent. Okay, so that one requires that. And the second term requires inference per iteration of data point. To circumvent this inference problem, again, we can use alternative objective functions, right? And the idea remains the same. Right now, you compute the gradient of the alternative objective instead of computing the gradient of the original objective, right? Or the maximum likelihood objective, I should say. Similarly, we can use approximate inference algorithms in order to get around this complexity of inference. Okay, so that's the good news, right? So the partially observed data case is easy to handle because again we are using the gradient descent algorithm for solving the problem. The final algorithm I'll cover is learning the structure of Markov networks. Okay, and this is an active research area, so I won't be able to cover all possible algorithms that are out there, as well as several new algorithms. So what I'll do is I'm going to give you just the principles rather than describing the algorithms formally as well as analyzing them formally. The first principle is that we have to use Bayesian scores. And the reason is that similar to Bayesian networks, complete graph is the optimal solution according to the max likelihood criteria. Okay, so we saw that in the context of Bayesian networks that a complete DAG is the optimal solution, right? And this similarly here, a complete undirected graph will be the optimal solution. And we don't want such a dense network. Okay, so in order to get around this problem, what we have to use is some sort of a Bayesian score where we attach a penalty term, and the penalty term is based on number of parameters. So smaller the number of parameters, the sparser the solution, right? And hopefully the better the solution. So there are two algorithms that are very popular in practice. The first algorithm, which was popularized by Della Pietra et al. In the 1990s, and I believe I'm sorry I have the name wrong, but this is a classic paper for inducing the structure of Markov networks from data, and it's essentially a greedy structure search algorithm. And the idea is as follows. What you do is you start with atomic features. So by atomic features, I mean features, if you have variables xi, right, then features are nothing but xi and xi bar. These are univariate features or atomic features. So you start with atomic features and then you greedily conjoin the features to improve scores. What I mean by conjoining the feature is that you take a feature xi and conjoin with it, let's say, feature xj, right? Or you take a feature xi bar and conjoin with it feature, let's say, xk, and so on. Okay, so you consider all of these features that are obtained by conjoining the original set of features, and greedily select one feature among them with a feature that improves the score the most. Okay, so you're using a Bayesian score and you will evaluate the Bayesian score based on these new features, right? And you select a feature that gives you the highest possible score. The problem with this approach is that you need to re-estimate the weights for each new candidate feature that you are considering. Remember, the structured learning problem includes parameter learning problem as a sub-problem. Okay? So each time you add a feature to your original set of features, you need to learn a weight for that feature. And this will have large complexity. Okay? So in practice, what people do is they use the following approximation. And the approximation is that you only update the weight of the new feature that you're adding to the model while keeping all the other feature weights constant. Okay, so that way the optimization problem is very easy to solve. Okay. The second approach that is quite popular, and this is a more recent approach, is to use logistic regression with L1 regularization for learning pairwise Markov network. And the idea is as follows. So you're given a Markov network, let's say over 4 variables, x1, x2, x3, x4. What I will do is I will learn a logistic regression classifier with L1 penalty for each variable xi, such that xi is the class variable and all other variables are features. Okay, so in this case, since I have 4 variables, I'll learn 4 logistic regression classifiers with L1 penalty. Okay, and what does the L1 penalty do? What the L1 penalty does, I should say, is it removes a large number of features because it helps you achieve sparsity. So when I say that it removes large number of features, what I mean by that is that it removes edges from this clique graph. Okay. So the idea is as follows. You run the logistic regression algorithm with L1 penalty for each variable x, assuming that x is a class variable and all other variables are features. Then you remove all edges that have 0 weights. If there is a conflict, in the sense that one logistic regression classifier, let's say over x1, is telling you that I should delete the edge between x1 and x2, while the logistic regression classifier at x2 is telling you that you cannot delete the edge between x1 and x2, right? How do you resolve this conflict? You can resolve the conflict by either taking the union of all the edges or by taking intersections of all the edges, or you can use some other criteria. Okay, so once you get the structure of this Markov network, you can do parameter learning on this Markov network by using any parameter learning algorithm. So in summary, in this lecture, we looked at learning algorithms for Markov networks. We looked at parameter or weight learning algorithms given structure, both generative as well as discriminative algorithms. Okay. We saw that if we use the maximum likelihood, or I should say if we use likelihood as our criteria, then the parameter estimation is very, very slow. Okay, so we saw multiple fixes for this. The first class of fix was to use approximate inference algorithms, and the second class of fix was to use alternative objective functions. We also saw learning algorithms when we have partially observed data. Okay, and finally, we saw 2 algorithms for learning the structure of Markov networks from data. Okay, and as I said, this is an active research area, and so we were not able to cover all possible algorithms. But the book is a nice reference. So, book by Kohler and Friedman, I should say, is a nice starting point or a reference for understanding new research on this topic.